everyone! Welcome to the A to Notes April lecture for Maths Extension 1. My name is Leo and I'm going to be your lecturer today. So before we begin, I want to quickly talk to you guys about A to Notes. So we are an educational company run by past students for students, and our ethos is all about accessible education. So we're all about helping you guys achieve your potential, and we do this through a bunch of resources that we offer. So we have heaps of free resources, including these lectures that you are watching right now. So we've been doing these since 2015. Obviously, because of COVID, we were disrupted and we had to move a bunch of our lectures online, but we've been continuing to do so, and we've been doing them for years now. So we have a bunch of study notes as well on our websites for you guys to download, free notes for all of your subjects. We also offer a discussions page where you can sort of talk with other students and you can get your questions answered. And we have a YouTube channel with heaps of online videos with topics, short-sized videos with revision material for all of your subjects. We have newsletters, we have an ATA calculator on our website, and we have articles as well. So we have a bunch of different offerings that we provide here at AT Notes. You can find out more on our website, or you can currently browse this website which you're watching your lectures on. There will be information up there as well. In addition to this, if you want extra support, we offer some premium paid resources as well. So we have a tutoring program called TuteSmart, where you can get live streamed interactive online weekly classes for your subjects, which are recorded, and you can go back and access any of those classes whenever you want. We also have printed study guides, as well as course notes, topic tests, and text guides in our bookshop. And we also offer Ed Unlimited, which is sort of our digital subscription service to all of our study guides that we have. So if you want to find out more about these services, you can also look around this website that you're watching this lectures on. There should be information up there. And I want to take the time to give some special thanks to our university sponsors. Obviously, without their support, these lectures wouldn't be possible. So I want to thank La Trobe University, RMIT, Deakin UTS, and Macquarie University. So shout out to our university sponsors as well. So if you've ever come to any of my previous lectures, you might already know me, but for those of you who don't, you might be wondering, who is this random guy speaking to you at the current moment? Well, as I mentioned, my name's Leo, and I graduated in 2018. So wow, 2018 was 5 years ago now, from Baulkham Hills High School with an ATA of 99.45. I did sort of a weird mixture of subjects, both humanities and STEM subjects, so that's listed here. I did Advanced English, Extension 1 Maths, Extension 2 Maths, Biology, Business Studies, and Modern History as well. And I'm currently studying a combined Arts and Law degree at the University of Sydney, which I'm currently really enjoying. And I achieved an overall HSC mark of 99 for Extension 1 Maths. So Extension 1 Maths, you either get a mark out of 50 if you do just Extension 1, but if you do it with Extension 2, they actually give you a mark out of 100. So I got a mark of 99 for Extension 1. I am a big lover of country music, and I'm currently learning how to play the banjo because I love country music that much. I also enjoy solving Rubik's Cubes, so I can solve up to the 5x5, and playing Valorant, the video game, even though I am very bad at the game, but still fun for me. So shout out if you guys have any interests similar to mine. Okay, so lecture overview. What's going to happen in the lecture today? We have 2 content blocks, which are 1 hour and 10 minutes each, and each block will have theory made clear and simple, examples to do together and on your own, as well as tips on how to ace each topic. So actually it should say content blocks of an hour each because this lecture is only 2 hours. But we'll also have a Q&A on Slido as well. So what's going to happen is during the live premiere of this lecture, I'll actually be in the comment section. I'll be monitoring your questions and I'll be answering them live while you're watching this lecture. So yeah, if you have any questions, pop them down below and I will go and answer your questions during the live premiere of this lecture. So yeah, I'll be monitoring your comments and replying to them. So specifically looking at today's content now. So our first block will be all about integration. So integral calculus, we'll be looking at extension 1 integration techniques, in particular integration by substitution. We'll also be learning how to integrate sine squared x and cosine squared x, and also how to do integrals that involve inverse trigonometric functions. We'll also be using integral calculus to find the area between two curves as well. In second content block, we'll be looking at differential equations, so we'll be introducing them, and then we'll be looking in particular at slope fields, also known as direction fields, and I think we'll wrap up with sort of an application question too. So first block is all about integral calculus, second block will be applications of calculus involving differential equations. Okay, so let's go to our first content block now. So integration. In the January lecture series, if you went to the January lectures, Krisha covered how to do integration in her Maths Advanced lecture, and I covered the foundational material for Extension 1 integration in my Maths Extension 1 lecture. So today we'll be moving on, and I'll be covering how to do integration by substitution with both definite and indefinite integrals, how to integrate sine squared x and cosine squared x, as well as integrals involving inverse trigonometric results, as well as how to find the area between two curves. So let's talk about integration by substitution first. So you might often hear integration by substitution being called U substitution. U in this case is a variable which we let equal to some part of the expression we're given to integrate. And when do we need to do this? Well, basically integration by substitution allows us to basically simplify a more complex integral into a simpler integral that is easier to solve. So just keep in mind, you don't always need to use U. By convention, it is U, but sometimes you might use like a different variable like theta instead, or something like that. So luckily in Extension 1, the question will always tell you when to use integration by substitution. So you will basically be told, use this particular substitution, and then you'll be able to just apply it to solve the integral. Unlike, of course, if you do Extension 2, they actually don't necessarily always give you the integral. You'll just be expected to kind of come up with the substitution yourself in some occasions. So keep in mind, if you do Extension 2, you might not always be given the substitution, whereas in Extension 1, you'll always be told, use this particular substitution. So the basic steps of how to do an integration by substitution question, you want to first of all start by differentiating the substitution, and then you want to change the integrand into an appropriate form using algebra. And in the case of if you're doing a definite integral, you want to change the limits as well. Once you've simplified everything in terms of U, you then integrate normally. And then in the fourth step, if you are working with an indefinite integral, you want to convert back to your original variable. So this is kind of complicated when you sort of write it out like that. It makes much more sense once we actually apply it to a question. So I like to mentally group integration by substitution questions into two types of questions. These aren't really formal classifications. These are just what I personally like to group them in. So we got chain rule type questions. So, or as I like to call them, dumb substitutions, because these questions can be done much more quickly using the reverse chain rule without actually needing to make a substitution. So yeah, I call them dumb substitution questions because you don't really need to use a substitution. However, if you struggle to use the reverse chain rule, obviously the substitution will make things easier for you. Although the flip side is that it is more time consuming. So it's much quicker if you just use the reverse chain rule. And then the second type are the non-chain rule type questions where the substitution is actually useful. to help you solve your integral, as opposed to just being able to just do it quickly using the reverse chain rule. So let's look at reverse chain rule type questions. So before we talk about that, let's just talk about the reverse chain rule. So remember, when we differentiate anything, we have to use the chain rule and multiply by the derivative of the function inside. So that's like something you learned in year 11 when you looked at how to differentiate. If there's a function inside, you need to also differentiate the function inside and multiply on the outside when you differentiate the entire thing. So basically, if you have like a function and we got a function inside, when you differentiate this, we get, not only do you just differentiate the outside like normal, but because it's a function inside, you also need to multiply with the derivative of the thing inside. So this is the normal chain rule. So that's what happens when you differentiate. But remember that integration is the opposite of differentiation, and it basically reverses what we've done with differentiation. So in order to reverse the process when you're integrating, if there's a function inside a function, you want to make sure that the derivative of the function inside is already being multiplied on the outside before we can integrate the whole thing. So this is known as the reverse chain rule. So basically, in other words, if you have a function, let's say you've got g of f of x, and there's a function inside, in this case, we've got f of x, you want to make sure that the derivative of the thing inside is already on the outside before you can then proceed to integrate this entire thing normally. And this accounts for the fact that, let's just say we wanted to differentiate this, we would get the derivative, but then we'd need to multiply by the derivative of the function inside. So that's what happens when you differentiate. But when you integrate, you want to make sure it's already in this particular form where the derivative of the thing inside is already on the outside before you can then proceed to integrate the entire thing. So it's basically just counteracting the chain rule, hence why it's called the reverse chain rule. So this is a really important principle you need to know when you integrate, because it applies for all functions. It doesn't matter what function we're working with. It doesn't matter if it's exponential, trigonometric, or just out like a normal like x to the power of n or something like that. It doesn't not matter. You need to make sure you are accounting for the reverse chain rule. Okay, so now let's go through some worked examples illustrating the chain rule type question. So let's just say we want to integrate x plus 2 times x squared plus 4x plus 1 to the power of 4. And we're told to use the substitution u equals x squared plus 4x plus 1. So the first step is you want to differentiate your substitution. So obviously here we're told to use the substitution u equals x squared plus 4x plus 1. So the first step is you want to differentiate u with respect to x. So we're differentiating the substitution. So in this case, the derivative of that is going to be 2x plus 4. Actually, this color is a bit hard to see maybe, so I might change the color. Maybe, yeah, that's much easier for you to see. So, yeah, we differentiated it. So, I will just, yeah, you have your substitution, then you differentiate the substitution. So I'm going to differentiate it with respect to x. So we got 2x plus 4. And now, for the purposes of the HSC, you can sort of treat derivatives like fractions. So what I'm going to do is I'm going to take the dx to the other side. So I'm going to say 2x plus 4 dx is equal to du. Now, the next step is we want to rewrite this entire integral in terms of u. So I can see that the x squared plus 4x plus 1, this thing inside, will just simply become a u. But I want to make sure I convert all the x's in terms of u. So I see here I have an x plus 2 dx. But here I have a 2x plus 4 dx. But I want an x plus 2 dx. But what I can see is I can divide both sides by 2. So I can say that du divided by 2 is just going to be x plus 2 dx. So now I got an x plus 2 dx. So I'm going to convert the integral all in terms of u now. So this thing is equal to the thing inside this here is u, so it's going to be u to the power 4, and the the x plus 2 dx here becomes the u over 2. So I can take the half to the front of the integral. So we got this, and now I can integrate it like normal. So this will become half times u to the power 5 over 5. Don't forget your plus c because it's an indefinite integral. But the thing is, I can't just leave it like this because this is in terms of u. I need to convert back in terms of x. So I'm going to say this is going to be 1 over 10. The u is going to be x squared plus 4x plus 1 to the power of 5. U squared, x squared plus 4x plus 1. And then I got the plus c. So this is my final answer for this integral. And you can see u to the power 4 is much easier to integrate than this entire thing. So yeah, that's how we basically do an integration by substitution question. You have your substitution, you differentiate, you rearrange to make all the x's in terms of u, and then you proceed to integrate like normal. Then remember, if it's an indefinite integral, like it was in this case, you want to make sure you convert back to the original variable. Okay, so this is part B. So we're told to evaluate this integral now without a substitution, just using the reverse chain rule instead. So this is a chain rule type question because you could have done this question without a substitution. So here we have a function inside another function. So inside the function here, we got x squared plus 4x plus 1. Now, with the reverse chain rule, if we have a function inside a function, we want to make sure that the derivative of the function inside is multiplied on the outside. So in this case, the derivative of x squared plus 4x plus 1 is 2x plus 4. So we want to make sure we got a 2x plus 4 on the outside. However, we don't have that. So we're going to have to do some bit of algebraic manipulation in order to get that to happen. So this is our integral. So I want a 2x plus 4 on the outside, but we don't have that. But what happens if I just multiply by 2? If I multiply this by 2, I'll get 2x plus 4 when I expand the brackets. But I can't just randomly multiply it by 2 because I'm changing the question. I don't want that to happen. So what's going to happen? What can I do to counteract that? Well, I can balance it out by dividing by 2 on the outside. So you can see here, what I've done is I've divided by 2 and multiplied 2 by 2 at once. So these things actually cancel. So I haven't actually changed the question. I've just simply done a bit of manipulation so that I can have a 2x plus 4 here. So yeah, this thing will become 2x plus 4 once you expand the brackets. And now this is in the perfect form where the derivative of the thing inside is being multiplied on the outside. So now I can just integrate this entire thing like normal. So raise the power by 1 and divide by the new power. So this will be half times x squared plus 4x plus 1 to the power of 5 divided by 5, which is going to be 1 over 10 x squared plus 4x plus 1 to the power of 5 plus c, because you don't want to forget your arbitrary constant when it's an indefinite integral. So you can see we got the exact same answer, but here we actually didn't need to use a substitution, which saves time because it's going to be less time consuming. So let's look at a second type now of a this is a non-chain rule type question. So this one you can't use the reverse chain rule to just directly do. This one, the substitution is actually useful. So we're told to evaluate x times square root of x minus 4 with respect to x using the substitution u equals x minus 4. So just like before, in extension 1, you're always given the substitution. So I'm going to let u equal x minus 4. So now what I can do is I'm going to differentiate the substitution. And then the derivative of x minus 4 is simply just going to be 1. So I can say that du equals dx, like so. And now my next step is to rearrange this integral and make all of the x's in terms of u. So what I can do here is inside the square root, the x minus 4 just becomes a u, but for the x, I can actually rearrange this so that I can say that x is going to be u plus 4. If I take the 4 to the other side and make x a subject. So here, this integral of x root x minus 4 dx, I'm going to convert all of these in terms of u. So x becomes a u plus 4, and the x minus 4 becomes a u, and dx just becomes du, because we said du is equal to dx. So this will become du. So now I can proceed to expand. So this will square root of u is just u to the power of half. So when I expand, this will be u to the power of 3 over 2 plus 4 times u to the power of half du. So now when I integrate that, it will become u to the power of 5 over 2 divided by 5 over 2, because I raised the power by 1, divided by the new power, plus 4 times u to the power of 3 over 2 divided by 3 over 2. So this will become 2 over 5 u to the power of 5 over 2 plus 4 times 2 over 3, which is going to be 8 over 3 u to the power of 3 over 2 plus c. But I can't just leave my answer like that. Remember that u is equal to x minus 4, so I need to convert everything back in terms of x minus 4. So this will be 2 over 5 x minus 4 to the power of 5 over 2 plus 8 over 3 x minus 4 to the power of 3 over 2 plus c. And that is how we do a question like this. And in this case, you couldn't actually use the reverse chain rule to do this question. So this substitution is actually useful in this case. Although there is ways to do this integral without needing to use a substitution, using clever algebra as well. I'm not going to go into it today, but if you are curious, try brainstorming a way you can do it. But there is ways of doing it, and I know how to do it, but I'm just not going to go into it right now in the purpose of saving time. Okay, so let's have a look at another question. This one was actually a past HSC question in the 2008 HSC. So the question is that we're going to use the substitution u equals log base e x, so ln x, to evaluate this definite integral. So if you want, you can just pause this video right now and go ahead and try doing it. To see if you could get it by yourself. But if you want to go through it, we're just going to go through it now. So this is the integral we're told to do, and we're told to use the substitution u equals ln x. So the way we do it this time, this is a definite integral. So there is an extra step we need to account for, which I'm going to point out when we do it. So we are told to use the substitution u equals l log base ex, so that's ln x. So when I differentiate that, so yeah, I'm just gonna, since the question uses log base ex, I'm gonna do it like that. So the derivative of log base ex is just going to be 1 over x, if you recall from when you learned how to differentiate ln x, differentiate logarithms. So therefore, I can say that du is equal to 1 over x dx, like that. And since this is a definite integral, I'm going to want to remember to change our limits. So I'm going to draw up this little table. So this is u, so this is x, and this is u. So our original limits were, we're integrating from e to the power e squared. And the way I'm going to find what our new limits is we're going to simply take the substitution and plug in our value for x to see what our new value of u is. So when e is equal to, when x is equal to e, log base e is just simply going to be 1. And when x is equal to e squared, log base e squared is simply going to be 2. So our new limits are from 1 to 2. So now we can say for this integral, that's equal to, if I have my new limits from 1 to 2, the 1 over x here, the 1 over x dx becomes a du, because 1 over x dx is du, so we got that. And now I just got 1 over log base e x squared, so that's just going to be 1 over u squared, like that, because u is equal to log base e squared. So this is the same thing as integrating u to the power of negative 2 from 1 to 2. So this will become u to the power of negative 1 over negative 1 from 1 to 2. And when I evaluate the limits, that's going to be, this is just negative 1 over u from 1 to 2. This is going to be negative half minus 1 over 1, which is negative half plus 1, which is going to be half. So our integral from our integral of 1 over x log base e x squared from e to e squared is going to be half. And in this case, this question is actually a chain rule type question, because you could have done this without having to use a substitution, because notice that there's a function here, and the function inside the function derivative is already being multiplied on the outside. So in this case, you could have done this without a substitution quite easily. Okay, here, okay, so we got another question now, and this is from the 2017 HSC paper. So we're told to integrate x over root x plus 1 from 0 to 3 using the substitution x equals u squared minus 1. So here, this is a non-chain rule type question, because this one, the substitution is actually useful for, because we can't just use the reverse chain rule directly, although there is a way of course, just doing this integral without a substitution. But yeah, we can't just directly use the reverse chain rule, so the substitution here is actually useful. So again, if you want to try this question yourself, you can pause this video and go ahead and attempt it, but we're going to go through it now. So I'm going to change the color so it's easier to see on this white screen. So again, same steps. We're going to, this time, the difference is x is the subject rather than u. So we're going to just use the substitution that the question tells us to do. So we're going to let x equal u squared minus 1. So I'm going to differentiate the substitution. So this time I'm differentiating x with respect to u. So this will become 2u. It's just going to be 2u when I differentiate x with respect to u. So now I can say dx is simply just going to be 2u du. So just the dx simply will just become dx. It will simply become 2u du. And again, this is a definite integral. So what I'm going to do is I'm going to make sure I change the limits. So my original limits in x were from 0 to 3. And then what happens when x is equal to 0? U will become 1. So u would be plus minus 1 normally, but for definite integrals, you don't need to worry about doing plus minus. You can just take the positive case. So it will just be 1. And when x equals 3, u squared will be 4. So therefore, u will be 2. So our new limits are from 1 to 2. So now this integral will become, our new limits are from 1 to 2. Here, x at the top becomes u squared minus 1. And at the bottom, we got root x is just u squared minus 1 plus 1. And the dx, well, that becomes 2u du. Like that. So when I simplify, what actually happens is this is u squared minus 1. Here, u squared minus 1 plus 1 will just be the square root of u squared. So it will just be u here. And this u cancels out with that u. So we actually get, if I take the 2 to the front, 2 integral from 1 to 2 of u squared minus 1 du. And this, you can see, is much easier to integrate compared to integrating this directly. So this will become 2, when I integrate, it will be u to the power of 3 over 3 minus u from 1 to 2. So I'll just plug in the limits now, and remember to be really careful when you do that. 8 over 3 minus 2, and don't forget to keep everything in brackets. So it will be minus 1 over 3 minus 1, like that. So this will be 8 over 3 minus 2, which is 2 over 3, minus a third minus 1, which is minus 2/3. So this will become 2 times 4 over 3, which is 8 over 3. So our answer in this case for this integral is 8 over 3. So you can see, same steps with integration. You just want to make sure you change the limits and convert all the x's into u's at the same time. So in the January lecture series, if you went to my lecture series in January, I demonstrated how we differentiate inverse trigonometric results. So just recall that when we differentiate inverse sine, we get 1 over root 1 minus x squared. And when we differentiate inverse cosine, we get negative 1 over root 1 minus x squared. And when we differentiate inverse tan, we get 1 over 1 plus x squared. So we also looked at these special results when we got x over a instead of just a regular x. So remember that when we differentiate inverse sine x over a, we get 1 over root a squared minus x squared. And that when we differentiate inverse tan x over a, we get a over a plus x squared. Oh, this should be a squared here. So it'll be a over a squared plus x squared. So don't forget there's an a in top. Well, this one doesn't have an a. So don't forget the squared here. Okay, so now that we know how to differentiate, we can go the other direction and we can, once we know how to differentiate, we can go the other direction and we can integrate. So now we can say that the integral of 1 over root a squared minus x squared, that's just going to be inverse sine x over a plus c. And when we integrate a over a squared plus x squared, we'll get inverse tan x over a plus c. And once these are the standard integrals, but you can go a further step and you can actually remember the reverse chain rule. So if you have a function inside the function, so instead of x, if we had a function here instead, you want to make sure that the derivative of that function, so if this was a function instead, we want to make sure that the derivative of the function is on the outside before we can then integrate the entire thing. So that's actually what appears on your reference sheet. So if you're curious about why your reference sheet wrote it like that, it's because they also incorporated the reverse chain rule into your reference sheet. So here, you get inverse sine. Here, Nessa for some reason likes to divide both sides by a. So here what actually happens is once you divide that by a, this will go away. So you just get 1 over a squared plus x squared. You get that result. I'm not really a big fan of that form. I just like this normal form here to get inverse tan x over a. But it's literally the same thing. It's just what happens if you divided both sides by an a. So same result. So if you have a function inside, you want to make sure you are multiplying by the derivative of the function inside before you can integrate. So here's an example of an integral that involves inverse trig. So we got 5 over root 9 minus 16x squared. So how do we integrate it? Well, notice that we can write 16x squared as, so here 16x squared is just 4x, the entire thing squared. So here we've got a function inside. Instead of having a regular x squared, we just got a 4x squared now. So also this 9 is going to be 3 squared. So here we've got a function inside. Remember, our form that we know how to integrate is 1 over root a squared minus x squared. We know that when we integrate this, it will become inverse sine x over a plus c. So here, but we have a function inside instead of x. So the derivative of 4x is going to be 4. So I want to make sure I have a 4 on being multiplied already. So I can take out this 5. So if I want a 4 up there, dx, I can't just add a 4. I need to balance it out. So I'm going to divide by 4 in the front. So I'm not changing the question. I'm just simply adding 4 then divided by 4 so that they cancel out. So now this is in the perfect form on what you have on your reference sheet, where you got the derivative on the outside and you got a squared minus f of x. This is like x squared. So this will simply become 5 over 4 inverse sine 4x over 3 plus c. And that's how you do an integral like that. Just remember, if there's a function inside, you want to make sure that the derivative of the function is already on the outside. In this case, we make sure that the 4x, the derivative of 4x is 4. That's on the outside. And then I can integrate it like normal using our result for differentiating integrals like that in this particular form. Okay, in the January lecture, I also talked about how to integrate sine squared x and cosine squared x. And I mentioned previously that in order to do that, we need to use the double angle formulas that we have for cosine. So basically, what happens is, remember with cos 2x, you can either write that as cos squared x minus sine squared, which you can then further simplify. You can further manipulate using the Pythagorean trig identity as 2 cos squared x minus 1 or 1 minus 2 sine squared x. Now, you can then make cos squared x a subject or sine squared x a subject and you get results. But remember, when you're integrating, you can also, the double angle formula applies. It doesn't need to be a 2x as long as you just make sure that the angle you get when you apply the double angle formula is half of what you had originally. So, for example, if you had cos 6x, that's still the same thing as 2 cos squared 3x minus 1, so long as the angle is half of that. So basically, when you when you have nx, when you rearrange it into this form, you just have to make sure that that's just double what you started with. When you make this a subject, for example, if we were trying to integrate cos squared 3x, this will simply be half 1 plus cos 6x, and we'll just have to change that into this because this thing is much easier to integrate compared to that. So just like I said, it comes from your cosine double angle formulas, which you learned in year 11, like that as expressed, and when you rearrange it, you can get these results. So luckily for you guys, these results are on your formula sheet, but it's still useful to know where they come from, because in the old syllabus, when I did my HSC, we basically weren't given these formulas on our reference sheet. We had to rearrange them from the double angle formula. So we had to know them by heart, otherwise we would be sort of screwed in an exam if we didn't know what the process was in order to integrate sine squared and cos squared. So here's a question. Let's say we wanted to integrate 2 cos squared 4x. Well, this thing is, if we take out the 2, we know that cos, when we say cos squared x, when we get cos squared nx, that's going to be half 1 plus cos 2nx from the double angle formula. So this is going to be half, we're going to change the cos squared 4x into half 1 plus cos. And remember, it just has to be double what that angle is because it came from the double angle formula. So it will be 1 plus cos 8x with respect to x, like that. So now the 2 and the halves cancel out, so we're just left with integrating 1 plus cos 8x, like that. And remember, this is a trig function, but inside the function, we actually have a function inside the function. So we want to make sure we are accounting for the reverse chain rule. So the derivative of 8x is 8. So I want to make sure that I have an 8 already multiplied on the outside before I can proceed to integrate. But I can't just randomly add an 8, I need to balance it out. So I'm going to divide by 8 as well at the same time. So here I haven't changed the question, 1 over 8 times 8 cos 8x is just going to be cos 8x. But now this entire thing, when I integrate, will become sine 8x. Because the integral of cos is sine. So when I integrate, this will be x. This will have a 1 over 8. And this entire thing here will become sine 8x. And it's an indefinite integral, so I want to make sure I do a plus c. So you can see my final answer here is going to be x plus 1 over 8 sine 8x plus c. And that's how we integrate results with sine squared x or cosine squared x. So here's another question. The derivative of a function is given. This is from the 2010 HSC paper. We're told that the derivative of a function f of x is given by f dash of x equals sine squared x. And find f of x given that f of 0 is equal to 2. So we're told the derivative, but we're asked to find the original function. So you can, of course, pause this video and attempt this question yourself, or I can, or you could continue watching and where we'll be going through it. So if we're told what the derivative is, which in this case is going to be f dash of x, which is going to be sine squared x, that's the derivative, we can say that the original function is what we're going to get when we integrate the derivative. Because remember, integration is the reverse of differentiation. So in order to integrate sine squared x, I'm going to apply a rearrangement of the cosine double angle formula. In this case, it's going to be 1 minus cos 2x. And here, I want to make sure the derivative of 2x is 2. So I want to make sure I have a 2 on the front, but I don't want to change the question, so I'm going to divide by 2 as well. So this will become half x minus half sine 2x, because this entire thing becomes the sine 2x. So this is going to be equal to half x minus a quarter sine 2x plus c, because it's an indefinite integral. But the thing is, we want to find the function because we're given extra information that when x equals 0, the function is equal to 2. So we could use this information to help us find what c is. So when f of 0 is equal to 0 minus quarter sine 0 plus c, and that's equal to 2. So sine 0 is just 0, so we know here that c is equal to 2. So therefore, our final answer for f of x is that it's equal to half x minus a quarter sine 2x plus 2. So that is our final answer for this question. So let's look at finding areas now. So remember from what you did in Maths Advanced that when you take a definite integral of a function from a to b, that actually gives you the signed area bound. If you're integrating with respect to x, it'll be bound between the curve and the x-axis. So the reason why we use this sort of symbol when we're integrating is actually an elongated sign for sum. So basically what's happening is you are taking all of these rectangles, oh, wrong color. So if you wanted to approximate, you could draw a bunch of rectangles. But with integration, that actually is when the widths of these rectangles are so thin that you get the precise exact area. So this is what's called like when you use these rectangles, it's what we call a Riemann sum. You don't need to know that technical term for the HSC, but basically that is how we basically get the area under a curve. We can use the definite integral. So in order to find the area between two curves, you simply need to, it's quite intuitive. Basically, if we got like a curve like this or something, when we integrate the top curve, we get this area. But when we integrate, so for example, if we're integrating from a to b for the top curve, we get this area. And if we integrate from a to b for the bottom curve, we get this area. So what actually happens is if you subtract the top area, which look like that, from the bottom area, you will simply just be left with this area between the curves, which is what we're trying to find. So the way we do it is we basically take the top curve, we subtract the bottom curve, then we integrate between the limits. So it's quite intuitive. You can see what's going on here. So yeah, for extension 1, you might be asked to find the area between two curves. So it's crucial that you know how to figure out which function is on the top and which one is bottom, because that's crucial. If you do it the other way around and put the bottom one first, then you're not going to get the right answer. So you want to be careful and make sure that you have the top function on top. So make sure if you don't have a diagram, quickly sketch a diagram just to see what's going on, because otherwise if you don't get the order right, you're not going to get the right answer. So the 3 important things you want to do when you're finding the area between two curves, you obviously want to find your points of intersection so you can see where the points intersect with each other. And these points of intersections will be your limits for your integral. Then you want to figure out which curve is on top so that you get the order right with your integral. And then you want to then integrate. So it's as easy as that. So let's do an example. Let's say we're told to find the area bounded between y equals x times 2 minus x and y is equal to x cubed. So obviously the first step is we want to find out where, so we're told to find the area bounded between these two curves. We want to find out where they intersect so we can figure out sort of what limits we're dealing with. So to solve them, we know y is equal to x times 2 minus x and y equals x cubed. So we're going to equate the curves to see where they are equal to each other. So x times 2 minus x is equal to x cubed, like that. So we can continue to solve them simultaneously. So I can take this to the other side. So I can say x cubed minus x times 2 minus x is equal to 0. Once I've taken this left-hand side to the other side. right-hand side. Now I can factorize out an x from both of these terms. So I can get x squared minus 2 minus x like that. And that's equal to 0. So I got x over x times x squared minus 2 plus x is equal to 0. So this is the same thing as x squared plus x minus 2 is equal to 0. And now for this quadratic, you can factorize it however you want. You can do the cross method, which is what I like to do. In this case, you can just think of two numbers that add up to give 1 and multiply to give negative 2. So those two numbers are going to be positive 2 and negative 1. So we can factorize it as x plus 2, x minus 1, like that. So you get x squared plus x minus 2 when you expand. And that's equal to 0. So therefore, positive intersections will occur when x is equal to 0, x is equal to negative 2, or x is equal to 1. So obviously these aren't actually the points of intersections, these are just the x values at the points of intersections. If you wanted to find the actual points of intersection, you could just plug it back in. You'll know that it will occur at 0, 0, negative 2, 8, negative 8, I mean, and 1, 1. But in this case, for the purpose of the question, you don't actually need to do that. You can just use the x values. That is fine for this question. So now we want to draw a rough sketch to sort of find out which graph is on top. So here we know this is the same thing as negative x minus 2. So this is a concave down parabola with x-intercepts at 0 and at 2. And it will look something like this. And the x cubed is going to be a cubic that looks like that. So this is a rough sketch, but you can see based on our information there's a point of intersection at 1, at 0, and here this is at negative 2. So it's not really to scale, but that's fine. It's just a rough sketch so you can see which one's on top and which one's on bottom. So just apply your curve sketching principles. You know cubics look like that. You also know this is a concave down parabola. So now the final step is we want to integrate. So we're trying to find the error bound between the two curves. So if I switch color, that's going to be this area here. This is the total area bound between the two curves. And to integrate, we want to figure out which one's on top and which one's on bottom. The problem is it changes because here the cubic is on top and here the parabola is on bottom. But on the right hand side of the y-axis, we actually get the parabola on top and the cubic on the bottom. So what you're going to do is you can do multiple integrals. You can split it up. So I'm just focusing on the left-hand side here. So the area is going to be the integral from negative 2 to 0 of the cubic on top, so x cubed minus x times 2 minus x. And we integrate that. And then we add that with the integral of, so we're going from 0 to 1. And this time the parabola is on top, so it'll be x 2 minus x minus x cubed. So basically we're going to find the area between 0 and 1 of the parabola and then take away the area from the cubic to find what the area is between the two curves. So we can proceed to integrate this now. So this will be integral from negative 2 to 0 of x cubed minus 2x plus x squared. And here we're integrating from 0 to 1 of 2x minus x squared minus x cubed. So when we integrate, this will become x to the power 4 over 4 minus 2x is the integral of that is just x squared, and this will be x cubed over 3 from -2 to 0. And here we got x squared minus x cubed over 3 minus x to the power 4 over 4 from 0 to 1. So just be careful when you're plugging in your numbers now. So here with our area, we got, when we plug in 0, this is nice, it'll just be 0, 0, 0, because all of these terms will just be 0. So it will be 0 plus 0, 0 minus 0 plus 0. Minus, this is where you want to be careful. Make sure everything's in brackets when you plug in -2. So -2 to the power 4 over 4. Then we got minus -2 to the power of 2 plus -2 cubed over 3. But this entire thing is in brackets as well, so be careful of that. And here we got plus 1 squared minus 1 cubed over 3 minus 1 to the power 4 over 4. And then here it's good because when we do 0, it'll be 0. So it'll be minus 0, minus 0, minus 0, like that. So everything's in 0, which is nice. So here we will get minus, this is going to be 16 over 4, minus, that's going to be 4, minus 8 over 3, plus 1 minus a third minus a quarter. So here inside the brackets, we get 16 over 4, which is just going to be 4 minus 8 over 3, which is going to be -8 over 3. So this will become 8 over 3 plus 1 minus a third minus a quarter, which is plus 5 over 12. So your final answer is 8 thirds plus 5 over 12. So this is saying this left area in red is actually 8 thirds, 8 over 3 in area, and this area on the right is actually 5 twelfths. So it's going to be 5 over 12. So when you add them together, the total area bound between the two curves is going to be 37 over 12. So that is our final answer. So this question wasn't too complicated. The only thing that could trip you up potentially is really the algebra and when you plug in numbers and the negative signs, making an error somewhere there. But the basic principle is the same in all of these sorts of questions. You just want to find where to intersect, then draw sort of a diagram to see what it looks like, and then when you integrate, make sure you put the one on top first, and then you subtract the one on the bottom, so that when you do the integral, you don't mess up and get the wrong answer. Now, the important thing is you can notice how with this first integral, I didn't even need to bother with considering the fact that it was below the x-axis. The formula works directly. Usually what would happen is when you have an integral below the x-axis, you actually get a negative number. But this formula is really good because when you have functions that are below the functions that are below the x-axis, what actually happens if we're just concerned with finding the area bound between them, if we take the area on top, let's say this area we got, if I change the color for that, here, let's say this was this is 4, so you get -4 when you integrate. And then we take the area on bottom, which actually will give you a bigger negative number because it's bigger in area. So let's say this was -6. When you integrate, when you do top minus bottom, you get -4 minus -6, which is going to be 2. So in actuality, the area between the curves is just 2. But because you were dealing with two negative areas, the negativities actually cancel out. And by doing top minus bottom, the top one is actually smaller than the bottom one. So where you do minus, it all works out. So you do, with this formula, with top minus bottom, you don't need to worry at all about whether it's below the x-axis or not, because of the way that the negatives sort of cancel each other out, and it will just give you a direct area. Whereas if you had another question where you didn't have finding the area between two curves, and let's say you were just asked to find like this area, you'd need to take the absolute value because it's going to be a negative number when you integrate. So yeah, this formula, you can see we didn't actually need to sort of worry about the fact that this was below the x-axis, because I could just directly integrate, just do the top function, which is the cubic minus the bottom function, and it all works out. You can see I still got a positive number here, 8/3. Okay, so now we can move on to our second half of the lecture, and we'll be looking at differential equations. So in differential equations, this is the syllabus. Remember the syllabus is your best friend. For the HSC, you want to treat it sort of like your Bible, because it outlines everything you need to know. And of course, yes, I can't examine anything outside the scope of the syllabus. So the differential equations topic from the syllabus has these following dot points. So we're going to cover the foundationals and the basics today. So we're going to look at differential equations, which can be abbreviated as DEs. So we'll be asking what is a differential equation, and we'll be looking at sort of how to solve a differential equation. So differentiation leads to equations in which derivatives appear. So basically what a differential equation is in fact just any equation that contains a derivative. So that's just a differential equation, any equation that has a derivative somewhere in it. So they naturally appear in many areas of science and technology. They're really useful. They're really helpful in our modeling of situations. So the way we solve differential equations is we will need to use integration to do that. And you need to differentiate between what a general solution is, as well as what a particular solution is. So a general solution is what happens, is basically a whole family of functions that will be able to satisfy the given differential equation, whereas a particular solution is what you get when you have a specific solution that will, so if you're given extra boundary conditions or initial values, extra conditions, you will get a particular solution. So let's go through that. So from the syllabus, you need to, this is a dot point, literally from the syllabus, to recognize that an equation involving a derivative is called a differential equation. So basically, a differential equation is an equation that has a derivative in it. So the following are all examples of a differential equation. So for example, y dash equals -7y, and y dy dx plus x equals 0, or x squared y double dash minus xy dash plus y equals 0. So these are all examples of a differential equation. So it doesn't matter if it's a second derivative or if it's just the first derivative, as long as it has a derivative in it, it is a differential equation. So remember that derivatives can be notated in various ways. So we have like this dash notation for first and second derivative. We also got dy dx d squared y over dx squared, like, or you've got the f dash of x and f double dash. So if you're curious why we use d squared y over dx, basically remember when we, I'll change it back to green. Here we go. So remember when we do d dx, we are differentiating with respect to x, so we know that that is going to be 2x. But whereas if we had y equals x squared, dy dx means the derivative of y with respect to x, so that's going to be 2x. So if we want to differentiate the first derivative we have, when we do d dx of dy dx, where here we can interpret that sort of like as d dx of y. So when I do d dx of dy dx, this will become d squared y over dx squared. Remember, the dx is just one entire thing, so we don't do d squared x squared, it's just dx squared. So that's where we get that notation for the second derivative. Okay. Just a side note in case you were curious. So we recognize that an equation involving a derivative is called a differential equation, and some terminology now. So the order of a differential equation is the number of the highest derivative that occurs within it. So, for example, if we have this differential equation y dash equals negative 7y, we know that this is the first derivative. So the highest derivative here is the first derivative. So therefore, it's a first order differential equation because the highest derivative is the first derivative. Whereas here, this is a second order differential equation because the highest derivative that occurs within it here is the second derivative. So in the HSC, you'll actually only be dealing with first order differential equations, but it's good to know this terminology so that when your teachers talk about first order differential equations, you know what they mean with the order. And of course, if you do maths later on at university, you'll be obviously looking at higher order differential equations. So here's the next syllabus talk point. You want to recognize that solutions to differential equations are functions and that these solutions may not be unique. So when we have sort of a normal equation like x minus 5 is equal to 2, the solution to that is x is equal to 7, which is a number. But with differential equations, the solutions to them, rather than just getting a number, the solution will be a function instead. So for example, if we got y equals, so if we had the differential equation dy dx equals 3x squared, how do we satisfy it? Well, one solution that solves this is y equals x cubed, because that satisfies this equation that dy dx equals 3x squared. So how can you tell if a function is a solution to the differential equation? Basically, you just substitute the function and its derivatives into one side and show it's equal to the other side. Alternatively, you can also substitute into each side separately and show that they meet somewhere in the middle. So I'll show you what I mean by that. So for example, we've got this differential equation dy dx is equal to negative x over y, and we want to show that y equals root 1. We want to show that y equals root 1 minus x squared. We want to show that it's a solution to this differential equation. So what I can do is I can differentiate. So dy dx is, this thing is the same thing as 1 minus x squared to the power of half. So I can take the power to the front, then drop the power by 1. But there's a function inside, so I need to make sure I multiply with the derivative of the function inside. So here, the derivative of 1 minus x squared is simply going to be negative 2x. So now, this 2 cancels out with that half, so we get negative x over 1 minus x squared to the power of negative half is just going to be dividing by root 1 minus x squared. So it's just the same thing as 1 minus x squared to the power of half, which will become simply root 1 minus x squared. Now, here's the thing. we initially said that y is equal to root 1 minus x squared. So when we get root 1 minus x squared here, that simply just is going to be, that simply is going to be x over root, no, it's simply x over y, because y is equal to root 1 minus x squared. So I can just, we know that y is equal to that, so that will simply become y. So we started with the left-hand side, that's equal to the derivative, but this thing is now equal to the right-hand side, because we literally showed that when we take the derivative of this function, we get negative x over y. So therefore, y equals root 1 minus x squared is a solution of dy dx equals negative x over y. So here's another question. So yeah, in this case, yes, it is a solution. Here's another question. Is y equals 2 over 5 e to the power of negative 2x a solution of the differential equation dy dx equals negative y? You can pause the video and try attempting it yourself to see if it is a solution or not. But let's try confirming it. So we know that the left-hand side of this differential equation is dy dx. And when we differentiate this function, we get 2 over 5 e to the power of negative 2x. But this, because when we differentiate e, it stays the same. But remember, there's a function inside the function. Here we've got e to the power of f of x. So the derivative of negative 2x is going to be negative 2. So this is going to be negative 2 times 2 over 5 e to the power of negative 2x. And the thing is, we know that 2 over 5 e to the power of negative 2x, this entire thing is just simply going to be 1y. So here we get negative 2y. And this is not the same thing as negative y. So therefore, no, it is not a solution. It's not equal to the right-hand side. So in fact, so in actuality, this is actually a solution of differential equation dy dx is equal to negative 2y instead of just negative y. So no, it's not a solution of this particular differential equation. Okay, so notice how here we have this caveat that these solutions may not be unique. Well, it's because they're part of your solutions. Your general solutions are part of a family of functions, and it's all got to do with that arbitrary constant when you do indefinite integrals. So for example, when you have y equals x cubed, that's a solution to dy dx is equal to 3x squared. But if you think about it, that's not the only solution to that differential equation. You can have a bunch of other solutions as well. For example, if you had y equals x cubed plus 1, if you think about it, that's actually a solution to the differential equation dy dx equals 3x squared, because it also works too. And if you have negative pi, if you had, like, I don't know, 1.14 to 13 or something like that, that also works. You have basically a whole bunch of solutions that are solutions to this differential equation. It's not unique. So in order to account for that, we can just say that x cubed plus c, where c is any arbitrary constant, that's the general solution to the differential equation dy dx equals 3x squared, because all of these will satisfy this differential equation. So you can see, if we sketch it, all of these graphs are part of the family of functions of the differential equation. And yeah, when you change what plus c is, it just shifts it up and down. But they're all part of the same family of functions. They all satisfy the same differential equation. So now let's talk about particular solutions. So we can actually find a particular solution, so one solution out of the whole family of solutions, when we're given extra conditions. So these extra conditions or extra parameters, we call them initial values or boundary conditions. So did you know, surprise, surprise, if you were paying attention, we actually did one of these questions earlier in the lecture. So remember this question we got when we looked at finding the function given the derivative is sine squared x? Well, guess what? This thing here is a differential equation, and that's the extra conditions. So those are our initial values or boundary conditions. So this thing here we got was our particular solution to this differential equation given these extra conditions. So remember the general solution we got when we were integrating was half x minus a quarter sine 2x plus c. So this is the whole family of functions that will satisfy this differential equation. But when we have these extra conditions, we got the particular solution. We found out that the particular solution of f of x is half x minus a quarter sine 2x plus 2. So let's try this question now. Find the particular solution of this differential equation, dy dx minus sine x times 1 minus cos x equals 0 if y equals negative 1 when x equals pi on 3. So let's just try making the first derivative the subject. So here we can say that dy dx is equal to sine x 1 minus cos x, like that, when I rearrange this equation. So this will be sine x minus sine x cos x, like so. And yeah, so we got sine x minus sine x cos x. And now to find the solution, we want to integrate, because to find what y is, we can say that this will happen when we integrate this entire thing with respect to x. Now the problem is this is relatively easy to integrate. That's just going to be negative cos. But how do we integrate sine x cos x? Well, just try to think creatively. What does this sort of resemble? Well, we know that when we have sine 2x, we get the double angle formula that's equal to 2 sine x cos x, that's equal to sine 2x. So what we can actually do is I want a 2 sine x cos x, but I don't want to change the question, so I can times it by half as well to balance out the fact that I am having O2. So that's going to be the integral of sine x minus half this entire thing will become sine 2x, like that. Now we know that with negative sign, the integral of negative sign is just going to be cos. But here we have a function inside a function, so we want to make sure we have a 2 on the outside. So what I can do is I can say this is equal to integral of sine x. We got plus a quarter times negative 2 sine 2x. Because this thing will become positive cos 2x when we integrate. But here I'm not actually changing anything because when I have a quarter times 2, I'll stay with half. So here, when I integrate, I get negative cos x plus a quarter. This negative 2 sine 2x becomes just a positive cos 2x when I integrate. So it will be negative cos x plus a quarter cos 2x plus c. But I'm not done here. We're told to find a particular solution. So we're told extra conditions. So here we're told that when x equals pi on 3, y is equal to negative 1. So we can use that when x equals pi on 3, y equals negative 1. So negative 1 is equal to cos pi on 3 is half, so negative half, plus cos 2 pi on 3 is going to be negative half plus a quarter times negative half. Because cos 120 is going to be, negative half. So cos 2 pi on 3 is negative half. So we've got plus c. So here we say that we have negative half. So negative half plus a quarter times. So actually, we can just make c the subject here. So c is therefore equal to negative 1 plus half. This will be negative 1 over 8. So plus 1 over 8. So that's going to be plus 1 over 8. It's going to be negative 3 over 8. So therefore, we can conclude that our particular solution is going to be, I'll write it here, it's going to be, a quarter cos 2x minus cos x minus 3 over 8. So that is our particular solution, which will satisfy this differential equation that dy dx minus sine x times 1 minus cos x equals 0. The particular solution that will satisfy this equation is y equals a quarter cos 2x minus cos x minus 3 over 8. Okay, so let's talk now about slope fields and direction fields. So this is just, keep in mind what we've been doing here is just the basics. You might think, why is this so similar to integration normally? It's because so far we've just been working with differential equations that just have an x in it. So that those ones you can just directly integrate. Later on, we're not going to go through it today, but in class, when you do this equation, you do this topic, and also later in, I believe, in future lectures, later in this year, we'll be doing more complicated differential equations. But basically, if you go back to the syllabus here, you can see that the syllabus specifies 3 different types of forms of differential equations you need to be able to solve. So far, we've just been focusing on the first one where everything's in terms of x, but later on in this topic, you'll be learning how to do differential equations that are in terms of y, or x's and y's at the same time, where you'll need to use a technique called separation of variables. But so far, we just are looking at the basics. Okay, so let's look at slope fields now. So this is another dot point of the topic which you guys need to be aware of. So sketching the graph of a particular solution given a direction field and initial conditions. So what is a slope field? What is a direction field? Let's just quickly talk about that. So a slope field or a direction field, they're the same thing, just different names for the same thing, basically tells you the slope of the function at that point. So the value of the derivative, the slope at that point, and you can only draw them for first order differential equations. But basically, using a slope field, you can sort of see what shape the graph should be in, because it tells you what the direction is, the slope is at that particular point. So for the purpose of the HSC, you need to know how to draw a direction field, how to tell the right direction field for the differential equation, and how to sketch a solution given a direction field. So how to form direction fields. Basically, as I mentioned, you can only draw slope fields for first order differential equations. So you'll be given a differential equation in the form of dy dx equals g of x of y. So this is just a fancy term saying an expression with x's and y's. Like you can have, for example, x over y. It doesn't have to be just, you don't have to have both of them. You can just be x. So, or you can have it all in terms of y, or you can have it in terms of x's and y's. It's just an expression involving x and y. And the way we can sort of determine the slope field is you basically sub different values of x and y in the coordinates into this equation to tell you what the slope is, and then you can use that to sketch your slope field. So in order to solve questions where you want to tell the right direction field for the differential equation, you can be smart about it by testing points, be smart with substituting particular points into the differential equation to see if it matches the slope field you're given in the question. So remember that the value of dy dx tells you the gradient of the slope at that particular point. So you can take into consideration whether x is positive in the quadrant or whether y is positive in the quadrant or not. And you can use that, use these signs, whether it's negative or positive, in order to get the right answer. So this is a bit confusing when I just say it like that. It makes a lot more sense when you actually do it in a question to see what I mean by testing points smartly. But yeah, just remember that the signs of x and y in each particular quadrant. So here's an example of a question you might be given in the HSC. They give you a slope field like this. This is a multiple choice question. They ask you which is the right slope for, which is the right equation for this slope field, this right differential equation. So you can pause the recording and try this question yourself if you want to. So we are going to go through it now. So if you want to try it yourself, you can pause it, but we are going to go through it. So we have 4 options and we can be smart with which points we can test. So just sort of consider the quadrants and the signs. So in the first quadrant, so here, we know that x is positive and y is also positive. So when we're dealing with this first answer, let's look at this first one. When we get a positive number divided by 3 times a positive number, the entire thing should be positive. So the derivatives should be positive, and we know positive derivatives are increasing. They go in this direction. But we know, looking at these slopes, all of them are pointing sort of downwards. They're decreasing. And that's not possible in the first quadrant where x's and y's are all positive. So therefore, we can eliminate A because it is not right. It's not matching with the signs. And similarly, if we look at B, if we take positive numbers and multiply them together and then divide by 3, that's still going to be positive. So in the first quadrant, these are all negative still. So we can eliminate B as well because it doesn't match with the signs. Because when we take 2 positive numbers and multiply, it will give another positive number. It won't be negative. So we know our options are either C or D. So there are several ways you can go about figuring out whether it's C or D. But one way is we notice that the difference between C and D is whether y is in the numerator or in the denominator. So if we have a look, at what happens when we change y. So I'm going to change the color. So let's take a look at this section here. So let's say x is fixed for a certain value. What happens when we change the value of y? If we increase the value of y, you can see it actually gets steeper. It goes from being flatter, it goes from like being flatter to going more and more steep. If we take a look like that. So this is what happens when y gets bigger. Now here's the thing, if y was in the denominator, as y gets bigger, this actual number will get smaller, won't it? Because it is, when the bigger the number you have in the denominator, the smaller the actual number is. But here, the actual number should be bigger. So we have a negative in front, so this is fine because all of these numbers are sloped downwards. It has a negative gradient, so it matches the signs right. But here, if we go, if y gets bigger and bigger and bigger, if the answer was C, your actual effect is that it will actually get flatter the more you go because it gets smaller, this overall number. Whereas here it gets bigger if y is in the numerator, because the bigger the y value is, the bigger the number. So in actuality, our answer here is going to be D, because we can just consider what happens when y increases. So that's another sort of way you can tell which is the right differential equation. You can look at signs. You can also consider the behavior as x increases or as y increases as well. So it's smarter to use the process of elimination to solve these types of multiple choice questions rather than figure out the exact differential equation which the slope field is representing. So don't go through each differential equation and sketch a slope field for it and see which one's the closest. That was way too time consuming. So in this case, it's actually going to be D. But yeah, if you were asked to sketch a slope field, what you would do is basically, you just have to go through each coordinate, say, for example, at 1, 1, plug it in. It'll be, the differential equation is going to be negative a third. So then you just sketch a slope with a third. And like, for example, at this point, 1, 2, you'd plug that in, it'll be 2/3, negative 2/3. So it'll be a bit steeper like that. So yeah, you just have to go for each point, then plug in the value into the derivative, then draw a little line like that to represent what the slope is at that point. Okay, so here's another question. We're told that a slope field representing the differential equation dy dx equals negative x over 1 plus y squared is shown below. And we're told to sketch the solution curve of the differential equation corresponding to the condition y equals 1 if x is equal to negative 1 on the slope field. So basically, we're given a slope field. This is what this differential equation looks like, and we're asked to find sketch a particular solution, given that when y is equal to 1, when x equals negative 1, y is equal to 1. So the solution will pass through this point. So there's no sort of like exact science to this. This is really rough, but the thing is, you kind of want to follow the slope, because it tells you what the slope is at that particular point. So you might draw something that looks like this, for example. It's not really exact, but you just follow the slope to get the solution. So a tip I have for you guys when you're sketching these is make sure when you draw your line, draw your sketch, don't cross any line because that means you're disobeying. So you shouldn't sketch something that looks like that, for example, where it crosses and breaks that line, because you are disobeying what the slope should be at that point. Make sure your drawing is parallel to the slopes and you're allowed to go through the entire line, just don't cross through like that. So you just want to make sure you are following the curve, following the what they tell you the slope should be at that particular point. So just don't cross through the slope. So here's another slope field we have for the differential equation dy dx plus x plus y equals 0. So this is like a graphical representation of what each gradient is at each particular point. So it can sort of give you what the solution might look like. And they asked us a solution to this differential equation that includes 0, -1. So at the point where it crosses here, so this is the point 0, -1, could also include what other point. So you can pause the video and try this question yourself if you want, and unpause it once you are done. So here we got 3 options. We got 3, -1, which looks like this. We got 3.5 and -2.5, which looks like that. And we got -1.5 and -2, which looks like this. And then we got 2.5, -1, which looks like that. So, -1.5 and -2 is over here. So we want to sketch a curve that passes through this point here. So if we follow the curve, we can see, follow the slope field, it will make us go all the way down there, which makes, we can't really go all the way there without disobeying the slope field and crossing the lines. So we can sort of rule out -1.5 and 2. And if we follow the slope, we know that it will sort of look like that. So can you go to this point? No, because you'll be crossing slopes. And if you can't even go to that point as well, because you'll be crossing slopes as well. So really, the only one that you can realistically sort of get to as a slope using the slope is actually 3.5, -2.5. So your answer for this particular question is going to be B, using this differential equation slope field. So yeah, this is kind of the drawing. Yep. Okay, so later on when you do this topic, you'll be doing sort of differential equations that are used to model the real world. So as I mentioned, differential equations are super powerful because they show up in a lot of areas of science, in the world where modeling is like in biology and chemistry, physics, sociology, economics. They show up in so many different disciplines and so many different fields. So they're really powerful. For example, even Newton's second law of motion, that force is equal to mass times acceleration, that is a differential equation because acceleration is the second derivative of displacement with respect to time. So yeah, that's a differential equation. So it's super useful. But let's just do sort of a simpler modeling question, just to sort of get your head around how differential equations can sort of be used to model situations. So let's say we have an Instagram model and she's calculating the number of photos to post to get the most likes. And she calculates the number of likes she earns per day is based on the number of photos she posts. So she calculates that, so if P is the number of photos she posts per day, and L of P is the number of likes she earns per day after posting P photos, let's say the rate of change, so the rate at which she's getting likes is equal to 216 minus 6P squared, and she wants to, so we want to solve this differential equation given that if she posts 0 photos, she gets 0 likes a day. So, yeah, we're given this initial condition that when P is equal to 0, L is equal to 0 as well. And then we want to find the value of P that produces the maximal number of likes and find that number of likes. So let's just solve this differential equation to find the particular solution to this question. So if we have dl dp is equal to 216 minus 6p squared, we can say that to find L, oh, I'm going to change the color back. We get that if we integrate 216 minus 6p squared with respect to p. So this will be 216p minus 6 times p cubed over 3 plus c. So this is 216p minus 2p cubed plus c. So we're told that when p is equal to 0, L is equal to 0. So therefore, 0 is equal to 0 minus 0 plus c. So therefore, c is equal to 0. So therefore, we can say that L is equal to 216p minus 2p cubed. Like so. So this is our equation for the number of likes which the Instagram model gets with respect to sort of how many photos she posts. So for part B, we're asked to find the value of P that produces the maximum number of likes and find that number of likes. So in this particular question, this is actually more similar to what you do in Maths Advanced with your maximization and minimization questions. So here we did differential equations, but here we are sort of doing a maximization question. And remember from Maths Advanced, when you are trying to find the maximum number of likes, that will basically occur when the rate of change, when you got a stationary point. So we can find the stationary point at when the LDP, when the derivative is equal to 0. So remember, at stationary points, you either have a maximum or a minimum, or in rare cases, you have a point of inflection. But you kind of want to find where the turning point is, because if you can show it's a maximum, then that's useful. So we'll try to find a stationary point, and then afterwards, we need to show it's a maximum. So let's see where this is equal to 0. So when this is equal to 0, we've got 6p squared is equal to 216. So p squared is going to be equal to 36. So p is equal to, you can do plus minus 6. But the thing is, remember, p is a number of photos that the Instagram model posts. You can't really post a negative number of photos. So, although technically you could say that's what happens if you remove photos, delete photos. But here, we'll just take the positive one because you can't post negative number of photos. But we can't really proceed without double checking this is going to actually produce a maximum number of likes. So we need to double check that. So there are two ways you can do this if you recall from Maths Advanced. You can either create a table of values or you can use the second derivative. So I'm going to sort of do both of these ways just to illustrate them in action. So let's go through the table of values. So if we drew up a table where we got P, we got dl dp, and we can figure out what's happening to L at that point. Oh, wait, I don't have space here. So I'll just do it here. So 6, you can just do numbers that are to the left and to the right of it. So you can do, you can post 5 photos or you can post 7. And we know at 6, the derivative, the rate of change of the likes with respect to the photo she's posting, when that's 5, 216 minus 6 times 5 squared is going to be 66. So 66 is a positive number, so it means that the number of likes is increasing at that point. Here is, but what happens when it's 7? So if you do 216 minus 6 times 7 squared, you get negative 78. So we know that when she posts 7 photos, the rate at which she's getting likes is actually decreasing. So this, if it goes from increasing to decreasing, we know that at this point, that's at the very tip of that, it's actually going to be a maximum. So therefore, it's a max. So that's if you use a table of values. What you could have done also is you could have differentiated this to find the second derivative. So the second derivative is going to be negative 6 times 2p, which is negative 12p. And when p is equal to 6 here, the point we're testing, the second derivative is going to be equal to, when we do negative 12 times 6, we get negative 72. So we know that the second derivative is negative. And remember, the second derivative tells us the concavity at that point. So if it's positive, it'll be concave up. If it's negative, it's concave down. In this case, it's negative, which means it's concave down, which means that it's going to be a maximum as well. So 2 ways you can show that it's a maximum. So therefore, we know that there is a maximum number of likes when p is equal to 6, but we're not done yet. The question asks us to find that number of likes. So we need to make sure we say when p is equal to 6, we know that L, which we found from the first part of the question, is 216p minus 2p cubed. So L is going to be equal to 216 times 6 minus 2 times 6 cubed. So when you do that, you'll get the maximum number of likes per day. So therefore, it's going to be 864. So therefore, your final answer is the value of p that produces the maximum number of likes is 6, and that number of likes is 864. So we know here that if she wants to get 864 likes a day, which is the most amount she can get, she'll need to post 6 photos, according to this modeling equation. So yeah, anything else and you'll get less likes. So the way to maximize the likes is you can post 6 photos. Okay, so that brings us to the end of the lecture, the formal end of the lecture. So I do realize we have some extra time. So we have around 10 minutes of extra time. So if you need to head off, feel free to head off. But with this bonus 10 minutes, if you're interested, we can actually go through how we can actually do that differential I mean, how we can do that integration question without needing to use a substitution. So if you're interested, this is some bonus content if you wanted to figure out how to integrate, for example, how to integrate this thing without needing to use the substitution x equals u squared minus 1. So what you could have done here was, if you didn't want to use the substitution, let me change it back to red so that's easy to see on this white screen. You can do an algebraic trick where you know how this is x and we've got a root x plus 1. What I can do is I can add 1 so that it resembles the bottom to get an x plus 1. But to balance out the fact that I'm adding a 1, I need to subtract a 1. So I got this particular thing instead. And this is exactly the same thing here because I just put plus 1 minus 1, it will cancel each other out. I will leave it with that. So I haven't changed the question. It's exactly the same. But now why I've done this is I can split this. So this is the same thing as x plus 1 over root x plus 1 minus 1 over root x plus 1. I've just split the fraction, which I can do like that. This is the same thing as that. But now, remember, x plus 1 divided by root x plus 1. Remember, x plus 1 you can say is root x plus 1 squared. So this actually just works out to be the integral of this thing will become just root x plus 1. Like if you rationalize the denominator, you get root x plus 1. Or if you just think about x plus 1 as what you get when you square x plus 1. I mean, when you square root x plus 1, this thing on the left is just root x plus 1. And here, this is just going to be x plus 1 to the power of negative half. And this thing here is just going to be x plus 1 to the power of half. And now, you can just directly integrate this. So this will be x plus 1 power 3 over 2 over 3 over 2 minus x plus 1 to the power of half over half from 0 to 3. So this will be 2/3 x plus 1, 3 over 2 minus 2 root x plus 1. And this will be from 0 to 3. And then you can just plug in your numbers and you'll get the exact same answer we got here, which is 8 over 3. So yeah, that's the other way you could have done it if you didn't want to do a substitution for this question. And similarly for this question here, let's say you wanted to integrate x over root x minus 4. I mean, integrate x times root x minus 4. What you could have done is a similar thing. So I'm going to change color. I'm going to use yellow, maybe. Yeah, cool. So if I wanted to integrate this, what I could have done instead was I could have, for this x, subtracted a 4 to make it resemble that, but then added a 4 instead. So that I don't change the actual question. So that when I expand this, I'll expand this with that. This will be actually x minus 4 times root x minus 4, which is x to the power of half. So that will be x minus 4 to the power of 3 over 2. And here it will be plus 4 root x minus 4, which is the same thing as x minus 4 to the power of half. So that when I integrate it, I'll just raise it to the power of 1. So it will be x minus 4 divided by x minus 4 to the power of 5 over 2 divided by 3 over 2. And do that. And then you actually just end up getting this exact same answer. So yeah, there are creative ways you can go about doing these integrals without needing to use a substitution. But of course, if the question tells you to use a substitution, you will have to use the substitution because otherwise you won't get the marks. So make sure if it tells you to use the substitution, do it. But if you see just an integral there, you can just do it without the substitution. But to be fair, in Extension 1, they will always give you a substitution. So it's only in some circumstances where there's like an integral where you can use a reverse train rule or do some other thing without needing a substitution, where they won't ask you to use a substitution, because in Extension 1 they always provide substitutions for you. Okay, so that bonus content done. That brings us to the actual end of the lecture. So thank you again for coming and for watching. I hope it's been useful, this little crash course on integration by substitution, and other integration techniques, as well as also this little heads up of differential equations. Thanks again for coming. All the best with your HSC. And if you do Extension 2, you can come along to my Extension 2 lecture, which I'm also taking. And we'll be focusing on Extension 2 integration in that. But if not, have a wonderful rest of the day. Thanks for coming. And yeah, good luck for Year 12.